Good morning. We were discussing the negative feedback system using an integrator. And as I said, negative feedback involves comparing actual and desired quantities. And based on the difference, continuously driving the output towards the desired quantity. That is to reduce the error between the actual and desired quantities. Okay. So the prototype is this. When we want a voltage amplifier, of course, a negative feedback can be used to control any quantity, and you can see like very commonly used in mechanical systems, electrical systems, and many other systems also. So this is the negative feedback arrangement. If you try to realize an amplifier, okay, a voltage amplifier with a gain K. Now what happens is if the input is a constant, then as long as this feedback is not equal to the input, the output will not be constant. Okay, because if there is some non-zero input to the integrator, it will be moving. Only way the output, and of course, if this VFB is smaller than VI, then the output will increase and vice versa. So the output will reach steady state when DC or constant input VI, then steady state V naught is K times VI. And this error, what will it be in steady state? It's going to be 0. Okay. So this business of the negative feedback driving that error to 0, that error is the virtual short of the op amp. Okay. In any negative feedback system, that error is that essentially equivalent to the virtual ground node or the differential input of the op amp, and that will be driven to 0, and it's because of this loop gain, because of this negative feedback action. Okay, it's not because the current somewhere is 0, etc., etc. So basically the negative feedback action will drive that error to 0. Okay, so when we say an op amp has a virtual short, it is a virtual short because the negative feedback drives it that way. Okay, and then we know some key parameters of this. The transfer function is K. So this is a first order transfer function with a pole at omega u by K, and this is also the bandwidth of the system because it's a first order system. And then for a DC input, step input, assuming you start from a 0 initial condition. Okay, obviously this is anyway a property of the first order system. So this is the reciprocal of the time constant. Now where does this omega u by K come from? We saw that the loop gain of this system is omega u by K times S. That is, this is the, if you have a prototype negative feedback system, the loop gain will be an integrator itself, right? The loop gain is of the form 1 by S. That's an integrator. Okay, so that means it is continuously adjusting the output in response to non-zero error. So now when you have this as the loop gain, the magnitude of L would look like this, and the unity loop gain frequency is omega u by K. Now this unity loop gain frequency is sort of the dividing line between having high loop gain and low loop gain. Okay, high loop gain, that's when you get all the good stuff because of negative feedback. Low loop gain, you don't get anything. Essentially you get an open loop system, right? Low loop gain means it's like having no negative no feedback, right? Because nothing is coming by. So this is why just for completeness I'll draw the phase, but you have to keep in mind, as I pointed out yesterday, in any negative feedback system, the transfer functions will be of this form. There will be some factor times L by 1 plus L, which also can be written as that. So as long as the loop gain magnitude is large, this additional factor will be close to 1. Okay. Right. So what is the meaning of very large loop gain? That means actually it is at those frequencies that you have virtual short. Okay. Because of that very large loop gain, that error voltage will be small, may not be 0, but will be very small. So approximately you have a virtual short. Okay. So basically this factor is what makes all the good stuff due to negative feedback possible. Okay. So this means that to have good negative feedback system, we want to maximize the loop gain magnitude, and we'll see that it's not so easy to do. We will have we will encounter some issues, and we'll see how to solve that. Now, because L is like this, our transfer function in this particular case is V naught by Vi is K, that one, right? So K is the gain that so if you plot magnitude of V naught by Vi, it will have K, I mean in a Bode plot sense, right? Of course, everything is changing smoothly. So this is K up to omega u by K. For a first order system, this is exact. That is the 3 dB bandwidth. The closed loop bandwidth is exactly equal to the unity loop gain frequency. Now, we will later come to more complex, more complicated systems because we want, because of practical limitations, we will not have only a first order system, we will have higher order systems. But there also approximately, if you had to just approximate the bandwidth, you can look at the unity loop gain frequency. Okay. And of course, it's not just something that drops out of the math. It's very clear that because when you have high loop gain is when you have ideal negative feedback type behavior. The unity loop gain frequency sort of defines the boundary of that behavior. Okay. So that is the closed loop bandwidth. Okay. So and of course, this is exactly equal for first order. That is where L of S is of the form the unity loop gain frequency by S. Okay. Now, things like, for instance, for this particular transfer function, closed loop DC gain is K and closed loop bandwidth is omega u by K. The product of these two equals omega u, but that is specific to this topology. Okay. So if you make some other type of amplifier, that may or may not be true, but it's always true that the closed loop bandwidth will be the unity loop gain frequency. Okay. So they should also tell you, like qualitatively, one of the most important things about these negative feedback systems, right? This comparison is the most important thing. Okay. Because finally, the input of the integrator will be driven to 0. Okay. So now, let's say you make some error in this comparison. Instead of Vi minus VFB, you may have Vi minus some scaling factor times VFB. then that is what will go to 0. Okay, so you'll have some error in the transfer function. Similarly, if some error gets added here because of noise or some other disturbances, then that also will appear at the output, the effect of that. Okay, so that input network of that negative feedback system, where you are essentially computing this error when you are doing this comparison, that has to be done precisely. Okay, after that it doesn't matter, you can drive it slowly or rapidly and so on. But because the result of that comparison is what will be driven to 0. Okay, so if you I mean, this is very clear, right? If you are driving and if your speedometer has an offset, you will be driving at the wrong speed. It's not that you don't know how to drive, but it's basically that you are comparing whatever the speedometer reads to the desired speed. Okay, this is fine. Any questions? Now, let me just show one more. Let's say I add a voltage Vx here at the output of that. Okay. What will be the transfer function from Vx to Vo? So, again, if I show it with the control systems, so this was my U, and let's say I have some V here. Y. What is Y by U? You know, it is G by 1 plus GH. What is Y by V? Huh? 1 by 1 plus GH. Again, you know the algorithm to get this, right? It's the direct path gain from V to Y divided by 1 plus loop gain. That's how it will be. So in our particular case, what is it going to be? In this case, V naught by Vx. What will it be? Please evaluate. What is it going to be? V naught by Vx. Huh? Okay. What will be V naught by Vx at very high frequencies? What will be V naught by Vx at very high frequencies? What do you guess it is? What is it? I couldn't hear. 1. Why? Yeah, basically feedback goes away, right? Vx appears directly at the output. Okay. So, if you evaluate it, you will see that this V naught by Vx will be S by, I'll write it like this. Okay. And this transfer function, this is another view of sort of negative feedback, right? What will this, the Bode magnitude plot look like of this? What will it be? What will it be at very high frequencies? 1. Beyond what frequency will it be 1? Omega u by K. It will do that. And you can see at low frequencies, that is well within the bandwidth of the system, the effect of Vx is suppressed. Okay. In fact, at DC, the effect of Vx is 0, right? So this is another view of negative feedback. You can think of this negative feedback as trying to follow Vi, right? This VFB will try to follow Vi because this is going to drive it like that. If you think about it from Vx to V naught, you can think of it as this noise cancellation, right? You have seen these headphones with noise cancellation and so on. Okay. What it does is it tries to feedback so that the effect of this is suppressed. But it cannot do it up to infinite frequency. It can do it only in a finite bandwidth. Okay. So within the bandwidth, you can have whatever error you want here, but it doesn't matter. Okay. So one of the ways of, one of the reasons you use negative feedback is also that any error added after this loop gain, after this integrator will be suppressed. Okay. So you can have at very low frequencies, you can have very large Vx, but V0, the transfer function from Vx to V0 will be very small. Okay. So this will be suppressed by the loop gain. And at very high frequencies, it's very clear there is no negative feedback. Vx just passes through to the output. Okay. These are all intuitively worthwhile knowing. It's not the calculation of the transfer function is not the important thing here. That is trivial, right? The basic block diagram calculation. The interpretation of the transfer function is what is important. Okay. Any questions? Now, so this is the prototype negative feedback system. Now, what can go wrong here? One of the possibilities is that, we have assumed that, for instance, while driving, you sense the speed. That is, you look at the speedometer and then you respond accordingly, right? So one of the very common things that happens, we will see, we'll translate it to the circuit domain, is delay. That is, the speedometer maybe, depending on how fancy the speedometer is, maybe it takes some time to compute the actual speed. Okay. So it is showing speed not at the current instant, but maybe let's say from 1 second ago. Okay. So let's just assume that. What will be the model for that? How would I model it in this system? Huh? So basically, I have to model some delay in this, right? So what I'll do is this delay, at least the motivation is clear, right? It's easy to understand why there could be a delay. Okay, so let's see what happens in that case. So again, we will work with the analogies and then this is the integrator that is trying to drive the output to the feedback is delayed. Okay, we'll come to this, but what would happen in real life? Let's say you're driving and you have this super fancy speedometer that is showing the speed from like 5 seconds ago. Okay, so you start from rest and you want to reach 40 kilometers an hour. So what is likely to happen? So okay, and then you start driving. Okay, this is your actual speed, and the speedometer shows you the same thing but delayed. Okay, so what is going to happen in this case? So first of all, initially, if it is an ideal delay like this, initially, this is very hard to believe, but you don't even know that you're moving. So because the speedometer is showing 0 up to this point, and then you keep driving. And at that point, the speedometer starts increasing. And then basically the error between the desired and the actual reduces. Okay. So now you're also responding to that, right? That was the idea. That is, you don't keep the you behave differently when your speed is like 39 kilometers per hour versus let's say 20 kilometers per hour, right? When it's very close to the desired speed, you will accelerate more gently. So that is this linear response that we talked about. Okay. So now you will maybe take your foot off the accelerator slightly and you slow down. But what happens actually? Finally, earlier, what was happening when you are getting instantaneous feedback? You would reach it as your speed increases, the error decreases. So you will accelerate more and more gently, and then eventually you will exponentially asymptotically reach the desired speed of 40 kilometers an hour. What happens in this case? What is that? I see drawing air pictures. Huh? Basically, the point is that somewhere you will, let's say you reach this. This is a possibility. You have reached 40, but the speedometer still says you are less than 40. So you will go on accelerating. Okay. You will go on accelerating, go beyond the target. And then this will also follow it. And at some point, the speedometer indicates 40. So then you start slowing down. You start slowing down, the speedometer would have been following you. And then in the other direction, when you reach 40, okay, what happens? The speedometer is still showing that you are above 40. So you will go under. Okay, so you will go over and under and so on. So basically there is, what is this called? Ringing. Okay, so you overshoot the target and then you ring around the target. Okay, this can easily happen because of delay. I have not analyzed. I mean, this equation can be written down and you can analyze it like you do. It's a little bit more involved because you have this exponential, but the algebra is slightly more complicated, but conceptually it is simple and it's also similar to something that you know quite well. Okay, so one possibility is if because of this delay, right, you will have this ringing. Okay. Now, if you can imagine that if the delay is very small, probably it doesn't matter, right? Is this okay? So this is what can happen because of delay in the negative feedback loop. Now, what is the remedy to this? Let's say now you become aware that you have delay because this kind of driving is quite uncomfortable, right? You keep doing this. So what is it that you would do as a driver? You can't change the delay. The speedometer does what it does. So what is it that you have to do to, let's say, reduce this or eliminate this overshoot? What will you have to do? Yeah. What, any ideas? What should I do? I mean, just think about again, the driving analogy is quite simple. So you want to reduce this overshoot. So what is it that you would like to do? What do you have to do? Hmm? Don't drive. Okay. Then basically, yeah, you have to accelerate more gently. Okay. That is, you know that let's say the delay is like 2 seconds and you accelerate gently enough that over those 2 seconds, the change of speed is not so much. Then you won't overshoot, or even if you overshoot, it's not be severely, right? Okay. Is this clear? So essentially, you slow down your system. That is because you have delay, you may have had a severe overshoot. Instead of reaching 40, you go all the way to 60, come back to 20, and you keep doing that. That's very irritating. That's not a nice way to drive. So then what you can do without changing anything else is that you simply accelerate more gently so that over the delay offered by that speedometer, you don't change the speed all that much. Then even if you overshoot, you will overshoot only by a little bit. Okay, or you may not overshoot. We'll see. Is this okay? So what is the in the amplifier? What is that equivalent to? So in this, I have TD and then I apply a step VI and then it overshoots severely. What is the problem with overshoot anyway? What is the big deal? Okay, driving it is uncomfortable. What's the problem with an amplifier overshoots? Noise. Why? Okay, but this is the transient part, right? The steady state will still be the same. Yeah, it could reach swing limits. Many things can happen. Like for instance, let's say you have your the power supplies that you use in the lab. They are also negative feedback systems because so that they hold the voltage to be some constant that you set, right? You set it to 6 volts or 5 volts or whatever. So now let's say you turn on the power supply, it reaches 8 and then comes back. And if it is connected to your circuit, who knows, your circuit could damaged. Could get damaged at that higher voltage, right? So many of these things can happen. I mean, that's just one example. So overshoot is not something you would want. So now what is it? So we don't want to overshoot. There is a lot of overshoot. So what should I do to the system to reduce the overshoot in this? Reduce omega u. You have to reduce omega u. That's the equivalent of accelerating more gently, right? Essentially, I have this ramp and then I reduce the slope of that ramp. Okay. So this always works. May or may not be desirable, but you can always make the system stable and well behaved by slowing it down. Okay. What is the disadvantage? The obvious disadvantage is that it slows down. That is, it takes longer to reach steady state. That may not be what you want. Okay. Or in the frequency domain, you can see that if you reduce omega u, what happens? Your bandwidth reduces. Okay. So that may not be what you want, but this will work. And you may have seen this in the lab also. If you have made these amplifiers, you will see some ringing, and then you put your finger on some node and it goes away. And it could be that the parasitic capacitance of your finger is actually slowing the circuit down, and that's why it goes away. Okay. You can always, I mean, in the worst case, you can always make the system well behaved by making it very slow. Of course, that's not always what you want to do. So now just some quantitative results, which I'll give without proof, which you can refer to other lectures for it. So basically, it turns out that if everything is related to how much the delay is, and the delay, it's not in absolute terms, right? It is related to the time constant of the circuit to begin with. Okay. So if this is less than 1 by E, E is the natural exponent, then it turns out there is no overshoot. And what is this? This can also be written as TD divided by K by omega u. What was K by omega u? It was the time constant of the ideal system. Okay. So compared to that, how much delay you have? That's what matters. Okay. So if this is between 1 by E and some number, there will be ringing. And then it turns out that if you have a delay to be larger than some value, we'll see how much that is, you will never recover. What happens is, let's say you want to reach 40 and you overshoot to 80 or more. Okay. And then when you come down, I mean, this is a little weird, but you will be going backwards because your speed has become negative. Okay. That is, the ringing can die out or it may not die out at all. With a sufficiently long delay, that's what is going to happen. So you will keep going back and forth forever. It will never reach steady state. Okay. Now let's just, I mean, it's a simple calculation. So you can find out what that what the value of the delay is. Okay. So how do you find out? So you have V naught by Vi. What is it in this case? What is V naught by Vi? Will it be? What is it going to be? Please calculate. Except? Okay. So what will you get actually? K times? Is it? S by Is this correct? Okay. So now, what does it mean to say that it will not reach steady state? One way of saying that is that the natural response of this doesn't die out, or in specifically, the natural response of this is a sinusoid of constant amplitude. Okay, it can even become worse, but let's say, and when do you get a constant amplitude sinusoid? This is a transfer function. So if you want to say that the natural response will be a constant amplitude sinusoid, what should you look for in the transfer function? What is the, okay, I give you a transfer function, how will you find the natural response? Huh? What is the natural response of the system? How will you find the natural modes of the system? You know what natural modes are, right? Natural response, natural modes. Huh? So basically it only depends on the poles of the system. If I have a transfer function, you look at the denominator. Then what? What were the natural modes of the system? Yeah, so you find the roots of the denominator polynomial. So natural mode means exponential that root times t. That is the natural mode. Okay. So the actual natural response will be some linear combination of these natural modes. Okay. So now what I am saying is, let's say that one of the modes is a sinusoid, a constant amplitude sinusoid. Okay. So what should happen to the transfer function for you to have a natural mode that's a constant amplitude sinusoid? Huh? So basically, there should be a root on the imaginary axis. Okay. So that is the denominator should become 0 for some s equals j omega naught. Is this clear? So then basically that j omega naught is the root of this. So exponential j omega naught t is the natural mode. I mean, of course, you will always have complex conjugate pairs, and then from there you will get the sinusoid. So please find out for this, okay, value of Td for which this denominator of s equal to 0 for some s equals j omega naught. Okay. It doesn't matter what that omega naught is. What is it? For what value of Td will you get this, and what omega naught will you get? Is it? What value of Td? Will be? Probability of omega naught and Td will be? Yeah. How do you do this? What do you get? Yeah. So you just substitute s equals j omega naught. What is this? Okay. Then plus by omega u by k. So obviously, for this to be 0, individually the real and imaginary parts have to be 0. The real part, this will be 0 when omega naught Td equals pi by 2, and of course plus n pi, that will also work. But basically we are looking for the smallest delay that will cause this, right? Any delay more than this is bad, but we just want to know what is the minimum delay that will do this. So now with this, what will you get? Because we want to find Td in terms of omega u, right? What is that? Omega naught is omega u by k. That's all. Okay. So basically, what are the limits? When omega u by k times Td is between 1 by e and pi by 2, you have ringing. And if it is more than pi by 2, you have instability. Okay. So you can see what happens. For very small values of Td, you will actually not have ringing. Okay. We discussed the possibility of ringing with the delay, but this is what happens. And then once Td, how much is 1 by E approximately? 0.36, right? 36 or 37 or something. So once you have that much, so again, the delay is 0.37 times k by omega u. That is 0.37 times the time constant of the ideal system. If you have that much, you will start to have ringing. Okay. And of course, ringing, you can tolerate a little bit of ringing. It's not that bad. Okay. But of course, not too much of it. So as you go on increasing the delay, at some point it becomes outright unstable. Okay. That is, if the delay becomes pi by 2 is approximately 1.5 times the sort of the ideal time constant, then it becomes unstable. Okay. But of course, long before that, it's unusable because you can tolerate a little ringing, but not too much. Now, what is this analogous to? At least these two cases. I mean, you know, some other thing where you see this type of behavior, right? What is it? What is it? I mean, you must have seen this in physics and very basic courses. Damping. Basically, this the very first one corresponds to what? Overdamping. Now, of course, this overdamping, underdamping, etc., refers to a second order system, right? Now, this is in general, like we have made it for some high order with some delay and so on. Okay. So, overdamping, which corresponds to zeta of greater than 1, and with ringing, that is underdamping, which is zeta less than 1. By the way, and in the middle, we also have this, right? We can have omega u by k times Td exactly equal to 1 by E. That corresponds to critical damping or zeta equal to 1. What is critical damping actually? What is special about it? We at critical damping, no. What is special about critical damping? What is it? What's special about it? It's the exactly. It's the fastest response you can get without overshooting. Okay. And that's true for zeta equal to 1. That's also true for omega u by k times Td equals 1 by E. Okay. So it is the, so as you go from over damping, as you reduce the damping factor, your response becomes faster. Of course, at some point it even starts overshooting, but this is the fastest you get without overshooting. Okay. So similarly here, some delay actually helps you in speeding up. Okay. But then of course, if you have too much delay, you start overshooting. So this critical damping is when you have the fastest without overshooting. So actually it is good to have some delay and you have this type of behavior. Okay. Is this fine? Now, if you have this idea of the basic negative feedback system needs an integrator, in reality, you will have this delay. Okay. This turns out is a fairly representative picture of all the negative feedback systems that you will see. Okay. Now we'll come to the conventional analysis you have done earlier, but this is something that you can keep in mind. Okay. This is okay. So in general, it turns out, I will justify this later. I'll just say okay, because many of these are margins, right? even quantities like phase margin. It's very easy to say, I mean, draw a boundary between it is stable or not. Okay, poles are in the right half plane or left half plane. That is very cut and dry. Okay, but margins are more subjective. I mean, all of you also may have different notions of margin. Some of you may leave for the train station 3 hours before the departure. Some of you may do it like 30 minutes before. Okay, so the idea of margin depends on the context. So here I'll say that TD, which is about half of the natural time constant, that is okay. By okay, we'll see how much it causes some overshoot, but that's typically within the tolerable region. And you will see this also corresponds to other common sense notions that you have about phase margin and so on. Okay. Any questions? You've already gone through analog systems and analog circuits, so you have this idea of stability criteria and so on. So I won't go through all of that, but I will relate these to the conventional stability criteria. Okay. Now, normally, I mean, you don't have these ideal delays. I showed the negative feedback system with ideal delays. What you have in circuits, you have these additional poles, zeros, etc. Okay. So how does this relate to that? So let's say we have, again, that is what you would have studied, right? So now, let's say that, okay, first let me do this. This is the ideal case, right? And then I have with delay. Okay. So now in the time domain, if I just plot the step response of L of S, what is the motivation for looking at the step response of L of S? So let's say you have some loop. Okay. Let's say the input is originally 0 and then it is stepped up. Okay. And let's say I break the loop here. If I step this up, what comes back here as the correction signal is the step response, right? Is this clear? So if I apply a step to the input, what is returned by the feedback is the step response. Okay. And of course, when you connect it together, it will modify the response in some way. So that's the reason for looking at the step response. So now what is the step response of L of S in the ideal case? Huh? Ramp. What is the slope of the ramp? Omega u by k. Now when you have delay, when you have this delay, what is the step response? It's the same ramp, but with a delay, right? So you will get this in parallel with that. So the slope here is also omega u by k. Okay. Now, just for completeness, let me also show this in the frequency domain, the magnitude plot. In the ideal case, it has a unity gain frequency omega u by k, and with delay, it is exactly the same because exponential, the delay has unity magnitude, right? Now, let's say I have additional pole. Okay, this is what you expect in circuits, right? You have some parasitic capacitor, like for instance, let me go back to the ideal. Okay, let me redraw it. It's fine. It's what I tried to make. Okay, but then there is a parasitic capacitance here, as you expect. So what you get because of this? You get an additional pole. Okay, so that is the type of model that you have. What is the step response of that L of S? Please calculate. Again, it's a simple calculation. What is it? What is the step response of that? How do you find the step response of this? What will you do? It is? How will you find the step response if you have some function like this? What will you do? Okay. You can just split it up into this partial fractions, right? And then take the step response of each part. Okay. Write it down. Please write it down and sketch the step response. What will you get? What is it going to be? Actually, different one of the factors. If you expand this out, what will you get? Omega u by ks, and I want to write it as that plus something. What will that be? Let's say I do this. So what should I put in the numerator? Huh? Minus omega u k p2. Okay. So that's what it will be. So omega u by Ks minus omega u by K times P2. Okay. What is the step response of the first part? Huh? Ramp. In fact, this may even be better written as omega u by K 1 by S minus 1 by S plus P2. Right? Okay. So what is the step response of that? Ramp. And when you multiply it by omega u by K, its slope becomes omega u by K. What is the step response of the second part? Exponentially. Okay. What is the step response of that? Just that part. What is it? Exponential. What is the step response of this? 1 minus. Okay. So the pole, I mean, this S plus P2, this is a common way of writing it, and it's also common to say the pole is at P2, but obviously the pole is in the left half plane, it's at minus P2. Okay. So what will this look like? What is the starting slope of that? What is the beginning slope of this one? What is the slope of it just after t equal to 0? P2. Actually, I think I made a, yeah. One by, right. Actually, there should be a, so the slope of that will be 1. So if you, it'll do that. Okay. So what is this minus that? What will you get? What will this height be? This is, please sketch this and see. It is omega u by K P2. So the difference between those two, what will it look like in the beginning? In the beginning, it will look flat, right? Because the two slopes are the same, it will look flat. And for a very large tree, it will look like that. So it will kind of smoothly do that. And what will be the horizontal spacing between these two? It is this height divided by the slope. It is 1 by P2. Okay. So you can see, even when you have this pole, earlier, what was the, so if I now put it on the same plot, I will get something like this, where this delay is like 1 by P2. Okay. So if you look at the step response of the loop gain, a pole does look like a delay. I mean, after some time, of course, with an ideal delay, it will stay exactly at 0 and then start ramping up. Now it will stay at 0, but then smoothly ramp up. Okay. So a pole, additional pole is like a delay. Okay. And please evaluate yourself. In fact, this is even easier if you have an additional 0, what happens? And with this, you can get insight into, first of all, what can destabilize the system and how you can stabilize the system and so on. So let's say you have this and you have a 0. You sketch the step response of that and then see what happens. Okay, we'll continue from there. Because see, earlier analysis, all of you who would have seen would be in terms of poles and zeros. Now I said something with ideal delay, but this does correspond to it. And then also you will see that this encompasses many cases altogether, that is higher order cases and so on. Okay. Any questions? I mean, there is a little bit of like very simple algebra, but the most important thing is not the working out of the algebra. That is very simple. The interpreting it is what is important. Okay. Please get into the habit of sketching figures so that you get insight into what's happening. Okay. Because it's very easy to get lost in the exponentials and other terms.